Alright, so we're going to continue on with stoichiometry, getting to some other types of problems besides the mole-mole problem we've seen. Our map to Moleville reminds us that there's more aspects to the mole than what we have done so far in stoichiometry. Mass is probably the most important aspect, and the most important stoichiometry problem we're going to look at is a mass-mass problem, very reflective of what we'll do in the lab, where you actually have to weigh your reactants and weigh your products and do the math that goes along with that. But don't forget, we also have particle information. Thanks to Avogadro's number, we can figure out how many particles are involved in reaction, and we're going to start looking at liters. Our next unit in here is going to be on gases, where we'll study this a little more in depth, but basically 1 mole of any gas at STP, which is standard temperature and pressure, will equal 22.4 liters. That's why I have highway 22.4 taking us to Leaderland. So again, we'll look at a little problem involving that, getting more comfortable with that before we move into our whole unit on gases. So this mass-mass problem, this is just kind of a diagram I drew up to show you what's going on. Essentially, you're going to be given an amount of mass. And, from that given mass, whether it be a measurement in the lab or the mass given to you in a problem, you're going to have to use the periodic table and change that into moles. All right, and now we are at the mole level, and of course from there we use the mole ratio to change from our given information to what we want to know about the substance in the reaction that we're looking to find an answer to. Once we use that, excuse me, we'll go back to mass using the periodic table, but this time for the new substance. So let's see this played out. Now there's going to be 2 different ways that I'm going to show you how to do this. One, the longer way, dimensional analysis, and also a shorter way, and you can choose which way works best for you. But here we see the recipe for when calcium reacts with hydrochloric acid. We get some calcium chloride and some hydrogen being produced. So the question asks, how many grams of calcium chloride can be produced from 127.5 grams of hydrochloric acid? Well, there's my given mass, and we can see this is a mass-mass problem because there's grams. Well, I take my given mass, 127.5 grams of HCl, and like many problems we've already done, I put that over 1. And then in my next conversion factor, I have to have grams of hydrochloric acid on the bottom because I'm converting. So grams of hydrochloric acid have to be diagonal. So that's my given mass, and I'm changing it to moles using the periodic table. And so whenever I use the periodic table, that of course is 1 mole of hydrochloric acid. The periodic table is always set at 1 mole. And so for the grams, I just have to use my molar mass. Hydrogen is 1.0, chlorine is 35.5. So when I add those together, that's 36.5 grams of hydrochloric acid in 1 mole. Now that I know the moles of my given substance, I am now at the mole ratio, and I need to change from what I know about, which is hydrochloric acid, and again, diagonal. And now I want to go to what I'm looking to know about, which in this problem is calcium chloride. So I change from hydrochloric acid to calcium chloride using the mole ratio. And so I look at my reaction. There's a 2 in front of HCl, so that goes there. And there's a 1 in front of calcium chloride, so that goes there. Now I have the final step where I need to go back to mass using the periodic table, but this time for my new substance. So here, calcium chloride. So again, going to the periodic table, 1 mole of calcium chloride, and I need to change that to grams. calcium is 40.1, and then 2 of the chlorines, again at 35.5, and that's going to add up to 111.1. So that is the setup of a mass-to-mass problem. And it's the same pattern every time. You're given a mass, use the periodic table to change it to moles, use the mole ratio to switch substances, and you go back to the periodic table for the new mass. And remember, mathematically, I will multiply the numbers across the top. So 127.5 times 1 times 1 times 111.1, and I'll get 14,165.25. On the bottom, 1 times 36.5 times 2 times 1, that's 73. So now I can find the answer, of course, with sig figs. And the nice thing is, however many numbers are in the starting measurement, that's how many we want in my answer. So I've got 4 numbers to start, 4 numbers in my answer. So it's 194.0 grams. So that's the longer way, just because it takes up more space lengthwise. But you can also do this by recognizing that, this is pretty much just all ratio math. A given mass is given to you, and then you're just using the ratio of molar masses from and the equation. So what you can do is take your given mass and just multiply that by one big ratio. Okay. Now, same rule applies. HCl is what we're starting with, so HCl has to go to the bottom of this big ratio. Calcium chloride is what we're trying to find out, so that goes at the top. And now I just look at my equation, and okay, I've got 2 in front of HCl. HCl we figured out was 36.5 on the periodic table. I've got 1 in front of calcium chloride, which we figured out is 111.1. So I just plug that information in my big ratio down here. So for hydrochloric acid, 2 times 36.5, and calcium chloride is 1 times 111.1. Essentially, I just smashed the long one down. I still have my mole ratio, and I'm just comparing the molar masses of those 2 substances in the same positions mathematically. Now, when you do the shorter version here, you do want to be careful and make sure you use your calculator correctly. You can still do it like above. You can multiply across the top and then the bottom and then divide. So 127.5 times 1 times 111.1. Or if you have a graphing calculator, you can do double parentheses. But either way, you should get the same answer, 194.0, either way you do this. So what I'd like you to do now is pause the video and try and do the next question. How many grams of copper produced from 250 grams of iron? And see if you can set that up, see if you can get the right answer. Then I'll show you how to get that. So hopefully you got 142 grams, 3 sig figs to start. That decimal after the 250 says count that 0. And so the periodic table for iron, 55.8. The mole ratio is 1 to 2. 1 for copper, 2 for iron in the balanced equation. And then copper's molar mass is 63.5. So long way or short way, we should end up with 142 grams. So that is the main stoichiometry problem. I do want to show you liters and particles because I mentioned that. So if you look at our next sample or example, here we have the recipe for ammonia again, nitrogen and hydrogen making ammonia. They're all gases, so we can involve liters here. So the question says, how many liters of ammonia gas can we produce from 122 moles of nitrogen gas? Well, I'm going to start my problem the same way. I have 122 moles of nitrogen gas over 1. And when I see moles, I should instantly think mole ratio. Since this is the moles of the stuff I know about, I want to switch to what I'm trying to find out. I want to know about ammonia. So I use the mole ratio to change moles of nitrogen into moles of ammonia. 1 mole of nitrogen, 2 moles of ammonia. And now all I do is end with our newfound fact that 1 mole of ammonia is 22.4 liters. So I change that moles of ammonia into liters using my new fact, 22.4. So for this one, mathematically, 122 times 2 times 22.4, 4 numbers to start, 4 numbers in my answer, 5,466 liters. The next question, asking about molecules, it's the same setup. I'm given moles, I'm going to use my mole ratio to switch, and then I'm going to end with a different fact. Instead of 22.4 liters, I'm going to end up with Avogadro's number. And so this is what that sample problem looks like. How many molecules of ammonia produced from 175 moles of hydrogen? So we've got a different mole ratio. Sorry. Hydrogen is 3, ammonia is still 2. School's over. So I've got 175 moles of hydrogen. I use the mole ratio to switch to ammonia, and then I use my old fact, 6.02 times 10 to the 23rd molecules in 1 mole. So 175 times 2 times Avogadro divided by 3, you should get 7.02 times 10 to the 25th. Or you could write 7.02 capital E 25. Alright, so these are the main sample questions. Now you want to look at that stoichiometry practice paper, and I will give you some hints on how to do those problems in the next video. Alright,